Hi everyone, I'm Ecem. I'm one of the organizers of NODE21 Challenge. Today in this short video, I would like to talk about how you could actually set up your Docker container to submit your own solution to the NODE21 Challenge for the detection track. All right, let me start first with the prerequisite. First of all, we are using grantchallenge.org to automate all the evaluation process. And for that, you need to have an account in Grant Challenge. And also you need to be a verified user on grantchallenge.org. That is very important because if you're not a verified user, you cannot submit your solution to NODE21. For that, you need to enter your information correctly, your name, your surname, your affiliation, and then you can request the verification to be a verified user. And then Grant Challenge team basically will take a look at your information and then they will approve it. So if you face any kind of problem, please let us know and we will take a look at it. Secondly, you need to have a Evaluators package installed. This is a package that is maintained by Grant Challenge and our template repositories are based on that. You could easily install this package by running pip install evaluators command. You need to have Git large file systems installed in order to be able to push and pull the model weights. You need, of course, Docker installed because you are going to wrap your algorithm in a Docker container because that is the only solution that we accept to be submitted to NODE21 Challenge. If you are using Windows, we highly recommend that you install Windows subsystems for Linux. This is also highly recommended by Grant Challenge team because it works pretty well as a development environment, or you can install Linux, and that already works very well. All right, so I would like to mention a few useful links. First of all, there is a general tutorial on how to create a Grant Challenge algorithm in the link here. It basically showcases a simple algorithm and shows how you could wrap that algorithm in a Docker container that is compatible with the requirements of Grant Challenge. So I would highly recommend you to take a look at this tutorial. And secondly, as I have mentioned before, you need to be a verified user in order to submit your solution to NODE21. So you could take a look at this documentation that explains how you could request to be a verified user in Grant Challenge. And lastly, very importantly, is that we provide two baseline repositories for one for detection, one for generation track. They are basically baseline repositories, but also they basically serve as a template, how you could basically also wrap your algorithm and submit your solution to Grant Challenge. So you could try to see how actually the input of the algorithm should be, how the output should look like, and etc., so that you could design your own algorithm and wrap it in also in a Docker container. All right. So we provided these two template repositories. So if you look at our challenge web page and you go to the details, you would see the template repository link here. And we provide some kind of a tutorial here that explains which kind of packages you need to install and how the overview of the baseline algorithm. So we explain the details about this baseline algorithms, and we explain how we could basically build, test, and export your Docker container. But I would like to still repeat a few things that are already mentioned here, but very important when you are developing your algorithm for the detection track. First of all, the detection track algorithms are expected to detect nodules from chest X-rays. They should read the chest X-ray image from a location /input/name of the image.mha, and they should return multiple predicted bounding boxes with an associated likelihood, and they should be written as an output to output/nodules.json. Nodules.json file is a particular basically format that is compatible with the Grant Challenge, and it's a dictionary and it looks like this. So here you see an example of nodules.json file, and here, for example, it is one item is called corner that basically shows this is one predicted bounding boxes, and it denotes the four location of the 4 points of this predicted bounding boxes. And it has an associated likelihood that is shown here as probability with 0.6. All right. So few important things is, first of all, when you submit your algorithm to Grand Challenge, the algorithm is expected to operate on a 3D image. What we mean by that is that we are going to provide a 3D volume where we stack several chest arrays together. So it means that if we stack 5 images together, your algorithm will receive 5 by 1024 by 1024 image volume, and it should operate on that. So it should basically read a single chest array slice by slice, and it should return a single nodules JSON file. The reason why we do that is because of the time efficiency. Otherwise, for every image, the Docker container needs to run, and it is a very time-consuming process because the model weights needs to be loaded every time you run the Docker container. So for that, we came up with that solution. So how you are going to identify which predicted bounding boxes belongs to which image. So basically how you will identify is with the Z coordinate. So in that example, here, if the last coordinate, the Z coordinate is 0, that will basically denote that this prediction belongs to the slice 0. And if, for example, here, if the Z coordinate was, for example, 5, that will say us that this predicted bounding box prediction belongs to slice 5. So you will use basically the last coordinate of this bounding box coordinates as an identifier of the image slice. And that's how we will use and how we will evaluate also your algorithm's performance. All right. Another important thing is that for our additional experiments, we expect the participants to implement the training, because that is going to be used once the challenge is over. We are going to perform these additional experiments, and we need each participant to implement this training function. So basically, you need to implement your training function that will receive an input and output directory. You will read the images and the associated label file from the input, and then you will write your model, final model weights as an output in the output directory. So actually pretty much what you only need to do is writing a function that implements training, but also it will be able to run in multiple phases. It might look a little bit complicated because it looks like there are multiple phases, but actually at the end, what you only need to do is implement the training function, and it's just a matter of how you start your training or how you start your test as an initial pre-trained model. So if there is no argument is given, it means that you load your model from model.pth file and perform an inference. If the train argument is given, then it means that you train your model from scratch, and the final model is saved as model_pre-trained pth file. If the retrain argument is given, you load the model weights from model.pth file and retrain it, and the final model is saved as model_retrain.pth. And if it is run on a retest phase, then you load your model retrained pth file and perform an inference. So as you could see here, it is just, you do not really implement much, but it is just, it denotes you where you start your pre-trained model. Right. Now I would like to go through a little bit the structure of the code from this template baseline repository that we have provided, that is published in GitHub, NODE21 challenge, NODE21 detection baseline. So I have already cloned this code repository. So on the left side, you see all the files. There are some script files that are test.sh and test.bat, export.sh and export.bat, and build.sh and build.bat. So bat files are for Windows and sh files are shell scripts for Linux. So if you already have installed Windows subsystem for Linux, or you're already using Linux, you could directly use the shell scripts. And if you are using Windows, you could use these bat files. So these are basically the commands that are building the Docker for you, testing it, testing whether your algorithm works as expected, and exporting the Docker container for you, so you don't have to write the commands yourself. So you could see here, basically, it just runs the build command for you, and the other files are also similar. that I will explain also soon. All right, so first of all, the main file that is pretty much doing everything is process.py file. So that's why I would like to go through this file, because this is basically the main file that will run your test and training. But if I summarize how the test works, is that we first have a class that is called nodule detection. And when you're creating an instance of this class, what you do is that you basically create your model. And if you want, you also, depending on which phase you're running, you basically load your pre-trained model or not. So basically in this initialization function, you're making your model file ready. Okay, then what happens is that depending on if you are running any kind of train, if you run with this train argument, so train or retrain, after you create an instance from your class, you are going to run the train function. Or if you are running this in test or retest mode, you are going to create an instance of your class, and then you're going to run the process function. So let's start first with the test mode. So if it is test or retest mode, we are going to run the process function. And that's actually the main thing that will happen when you upload your container to Grand Challenge, because what you want is that you want this to run on the test mode, which is basically will load your model PTH file, and then it will perform an inference on the test images. So this process function is a function from evolutors, and what's going to happen is that it's going to call the predict function. So let's look at it, what's happening in the predict function. So it basically receives a simple ITK image, and then it will load your model. It will read your images, performs a prediction, and then it will return these predictions to be saved as nodules.json. At the end, this is what we want to do. You basically receive an image, you perform an inference, and then you return the prediction. That's how we could summarize it. But let's go through one by one. So first of all, as you see here, you get your model and you put it in the evaluation mode. And then you read your image data, you convert it to an NumPy array. And then you go through your image data. As you could remember, we are going to provide a 3D volume here where we stack multiple chest arrays together. So if you are, for example, are going to give 200 chest arrays, it means that you are going to receive 200 by 1,000, 200 by 1,200 by 1,024 image volume. It means that you need to iterate over each slice and read the chest array, perform the prediction, and then basically put all these predictions into results list. So this is what's happening here. Basically, it reads the first chest array, and then it normalizes the chest array, performs a prediction here. As you could see, it gives this tensor image to the model file and gets the prediction. And as you could see here, we also perform some post-processing on the predictions, which is non-max suppression technique. And then we get the predictions after the post-processing technique. And then we basically collect all these predictions for each chest array in the list of results. And once we collect all these predictions, then we are going to convert these predictions to a nodules.json format, and then we will return this nodules.json format data directly. And evolutors will directly save this nodules.json format dictionary for you to output /nodules.json. All right, so this is basically your test phase. When you also upload your container to Grand Challenge, it will run this predict function after loading the model PTH file for you. So what's going to happen if it runs on a training mode? So we implement the training function here. So let's say that the number of epochs is defined as 50. Actually, in the original code, we have given the number of epochs as 1, so it's easier to debug everything. But please make sure that you give the number of epochs as large as possible. So maybe you could just define it as 50, and make sure that you actually save your model PTH file, model retrain file as very frequently, because it could be possible that we just stop the training process anytime. So you have to make sure that you're actually saving your model weights frequently. And even though we stop in the middle of the training, we still have a good model weights that we could work with. So what we do here is that we have our model file, we put it in the train mode, we create our data set from input directory. So input directory should contain a folder called images that contains all the images, and it should contain a metadata CSV, which is basically the label file. This is also the similar format that what we have provided in Zenado release for our data set. So then what we do is that we define our optimizer, learning rate scheduler, and then we started to train as a 50 number of epochs here. So we update our model weights, we update the learning rate, and then we save the model here as model retrained PTH file. So this is what you do for you. Basically, you have your input directory, it trains the model and saves the model to your output directory as model retrained PTH file. All right. So I'm not going to go over really this code much because I think they are already self-explanatory. This is just receiving the image prediction, the nodule predictions and converting it to grand challenge format for nodules JSON file that we have called here in the predict function. We have our post-processing code where we define it in the post-processing PI file that are basically non-max suppression technique, and it calculates also intersection over union. So you could take a look, but I think that's already that are already self-explanatory as well. And I think that's pretty much everything. As you see here, you only need to implement your training function, and the difference, if you are given, for example, retest, retrain, or train mode, is just a matter of which pre-trained model you are starting with, basically, and you don't need to do much about it. All right, so now let's look at how we could build, test, and export a container. I have already cloned the repository here, so you can see that all the files are here already. So in order to build a container, you need to run the build sh command. So it's already built a container and it's tagged with nodule detector latest. So now we know that build is successful and there is no any problem. Now I'm going to run a test sh command, which will test whether the container works as expected. So first, let's look at what test sh command does. So in this shell script, what it does is that it runs your container, it produces nodules JSON file, and it checks whether the nodules JSON file that was produced by your container is the same with the expected output JSON. So we have updated this expected output JSON file with the nodules JSON file that should be produced by our container. So it kind of tells us whether the container works as expected or not. If the expected output JSON and nodules JSON file are the same, then it will return that test is successfully passed. So let's run this command now and see whether everything works correctly. Perfect. It produced already the results, and as you see, the test successfully passed because the expected output JSON is the same what was produced by the Docker container. Perfect. So now the test successfully passed, but you might also want to see the output that was produced by your Docker container, because when you run test sh command, it is not writing the output anywhere. So you could also alternatively run the Docker run command. So I have already run that command before. So as you see here, it's a Docker run command. I assign the GPU, and then I basically map the input directory and output directory, and then I'm going to run. And nodules JSON file that is produced by this Docker container will be written to the output directory that was given in the command. Perfect. So it's basically run the container now and wrote the output to the output directory. So the output directory was basically this one. Yes, this was our output directory. So it has written modules JSON file on it. So let's look at it, what it is inside this modules JSON file. And as you can see, it produces the output as we expected. Perfect. So now we can basically run the container, test the container. We have built the container. We could also run the container in a training mode and see whether everything works as expected. So in order to do that, you basically need to run the command with the train argument. And as an input folder, you need to map it to your training images folder. So inside this training images folder, you need to have an images folder, so as a folder called images, and you need to have a label file that is metadata CSV file. And then you could run basically your command, and it will start training your model. Perfect. So it says training start, and it already started training. I'm going to stop this now because otherwise it will take a lot of time. But we already know that now it works. And once the training is done, it will actually frequently write the model retrained PTH file to the output folder that was given in the Docker command. Perfect. So the only thing we need to do now is basically export the container. So for that, we could run export sh command. So when you run this command, it will take quite a lot of time, but basically at the end, it will write the container with an extension tar.gz. So once this command is done, you will already see that your container is written in the output directory. And basically, you could then upload this container to Grand Challenge and then submit that as an algorithm, where we will explain this procedure also in another video.